There is a simple limit built into the universe, and it has nothing to do with walls or edges. It has to do with time. Light moves at a finite speed, and the universe has existed for a finite duration. Because of this, there is only so far we can see. Beyond a certain distance, light has not yet reached us, and so those regions remain invisible, not because they are hidden, but because the universe has not been around long enough for their signals to arrive. This boundary is known as the observable universe. It is not the size of the universe itself. It is the size of our view. Everything beyond that horizon may still exist, unfolding according to the same physical laws, simply disconnected from us by time and expansion. When scientists first realized this, the idea of parallel universes quietly entered physics, not as speculation, but as a consequence of scale. If space continues far beyond what we can observe, and if the laws of physics are uniform throughout that space, then distant regions may look much like our own. Matter would clump under gravity, stars would ignite, galaxies would form. Chemistry would follow the same rules. The only difference would be location. These regions would not overlap with us or interact with us. They would simply be elsewhere. Now consider size. Even within a region as large as our observable universe, the number of ways matter can arrange itself is enormous, but not infinite. If space itself is infinite, or even vastly larger than what we can see, then eventually those arrangements must repeat. This is not philosophy. It is combinatorics applied to cosmology. Given enough volume, patterns recur. Somewhere unimaginably far away, there could be a galaxy arranged almost exactly like the Milky Way. Somewhere else, a planet orbiting a star like our Sun. Somewhere else, conditions similar enough that history unfolds in a way that strongly resembles our own. This idea describes the most conservative form of a multiverse. Not separate realities with different laws, but one enormous universe containing many distant regions, all governed by the same physics. Cosmologists sometimes call this the simplest multiverse because it requires no new mechanisms, only space that extends beyond our horizon. Observations support the assumptions behind this picture. On the largest scales we can measure, the universe looks remarkably uniform. Matter is evenly distributed. Space appears flat. There is no preferred direction and no central point. These features suggest that whatever shaped the early universe operated over regions larger than the part we can now observe. The strongest evidence comes from the cosmic microwave background, the faint radiation left over from the universe's early hot phase. This afterglow fills the sky almost perfectly evenly, with tiny variations that trace the seeds of future galaxies. The uniformity of this radiation tells us that distant regions of space were once in close contact, sharing information and energy before being pulled apart by expansion. To explain this, cosmologists developed the theory of inflation, which proposes that space expanded extremely rapidly in a tiny fraction of a second early in cosmic history. This rapid expansion would smooth out irregularities, flatten space, and produce the near-uniform conditions we observe today. Inflation does not merely describe what happened inside our observable universe. In many models, it implies that the region we see is just a small part of a much larger expanse created by the same process. Already, without invoking anything exotic, we arrive at a striking possibility. Our universe may be far larger than what we can ever observe, and within that vastness, regions like ours may repeat. Parallel universes, in this sense, are not mysterious duplicates stacked beside us. They are distant outcomes of the same cosmic rules, separated by distances so great that no signal could ever cross between them. But this is only one way the idea of parallel universes enters science. There are others that do not depend on distance at all. Some arise from the mathematics of quantum mechanics, where outcomes do not settle into a single result until interactions occur. Others emerge from deeper theories about how space itself behaves at the smallest scales. To reach those ideas, we must leave the scale of galaxies and expansion and move inward, to experiments performed in darkened laboratories, to particles that behave like waves, to situations where reality appears undecided until it is measured. The most unsettling arguments for parallel universes do not come from the farthest reaches of space. They come from the smallest things we know, and from a question that physics has never fully resolved. What is a particle doing when no one is looking? To explore that, we will step into a quiet room, face a simple experiment, and watch how possibility becomes fact. That is where the next layer of parallel universes begins. Before shrinking the universe down to particles and probabilities, it helps to understand how modern cosmology arrived at a universe large enough for parallel regions to even be plausible. The idea did not begin with advanced mathematics or particle physics. It began with a slow dismantling of the assumption that our location is special. For most of human history, Earth was assumed to sit at the center of everything. The sky revolved. The stars were fixed. The cosmos was small enough to feel personal. That view collapsed gradually. Copernicus displaced Earth from the center. Galileo showed that the heavens were not perfect or immutable. Newton demonstrated that the same force pulling an apple downward governs the motion of planets. With each step, the universe grew larger and less centered on us. The final shift came when space itself stopped being static. Einstein's theory of general relativity revealed that space and time are dynamic, shaped by matter and energy. They can stretch, bend, and evolve. When Edwin Hubble observed that distant galaxies are moving away from us, and that the farther they are, the faster they recede, it became clear that space itself is expanding. The universe was not eternal and unchanging. It had a history. Tracing that expansion backward leads to a hot, dense early state. Not a point in space, but a condition everywhere. As the universe expanded and cooled, particles formed, then atoms, then stars and galaxies. This picture fits observations extremely well, but it leaves puzzles behind. Why does the universe look so uniform in every direction? Why is space so close to geometrically flat? Why do regions on opposite sides of the sky look nearly identical even though, according to simple expansion, they should never have been in contact? Inflation was proposed to answer these questions. In this theory, a brief period of extremely rapid expansion occurred early on, stretching space so quickly that regions once close together were pushed far apart. This would explain the smoothness of the universe and the tiny fluctuations seen in the cosmic microwave background. Those fluctuations match inflationary predictions with impressive accuracy. Inflation is not proven, but it is strongly supported by data. Once inflation is written into the equations, something unexpected appears. In many versions of the theory, inflation does not happen once and stop everywhere. Instead, it ends locally. Quantum fluctuations cause inflation to shut off in some regions while continuing in others. Where inflation ends, a hot expanding universe like ours begins. Where it continues, space keeps stretching. This process can repeat endlessly. The result is a cosmos that produces many separate expanding regions, each born from inflation, but isolated from the others by the ongoing expansion between them. These regions are often called bubble universes. They are not floating in space. They are space. Each bubble contains its own expanding cosmos with its own history. This picture is known as eternal inflation, and it leads naturally to another sense of parallel universes. Each bubble universe may share the same underlying laws of physics, but the details can differ. The strengths of forces, the masses of particles, and other fundamental values may vary slightly from one bubble to another, depending on how fields settle as inflation ends. This is not introduced to make the universe feel strange. It emerges from the mathematics of fields interacting with expanding space. Once the possibility exists, it changes how physicists think about certain questions. For example, why does our universe have the particular properties it does? Some values appear finely tuned. Small changes would prevent stars from forming or chemistry from stabilizing. In a multiverse, these values need not be uniquely determined. They may simply be local outcomes among many possibilities, with observers naturally finding themselves in regions where complexity is possible. This idea is known as anthropic selection. It does not explain the laws themselves, but it explains why we observe certain values rather than others. It remains controversial, not because it is illogical, but because it is difficult to test. Physics prefers explanations that make precise predictions. The multiverse challenges that preference by introducing vast ensembles where probabilities become subtle. Scientists have looked for possible evidence of other bubble universes. In principle, if two expanding regions collided early in their histories, the interaction could leave a faint imprint on the cosmic microwave background. Researchers have searched for such signatures. So far, none have been confirmed. Inflation also predicts primordial gravitational waves, ripples in spacetime that could be detected indirectly through polarization patterns in the microwave background. These searches continue, patient and cautious. At this stage, parallel universes arise not from speculation, but from extending well-tested ideas carefully. A large universe naturally contains distant regions beyond our view. Inflation, if eternal, naturally produces separate expanding domains. These ideas remain under active investigation, guided by observation wherever possible. But there is another route to parallel universes that does not rely on cosmic distance or expansion at all. It comes from quantum mechanics, the theory that governs the behavior of particles in fields at the smallest scales. Unlike cosmology, which stretches outward, quantum theory folds inward. And in doing so, it raises a different kind of multiplicity. To understand it, we must abandon the idea that reality always has a single, well-defined outcome before we look. We must face experiments where particles behave as if multiple possibilities coexist, and where observation itself plays a decisive role. To reach that point, we step away from galaxies and background radiation and into a quiet laboratory, where a single particle travels toward a barrier with two narrow openings, and reality hesitates. That is where we go next. Quantum mechanics was born from this kind of strangeness. It is a theory of probabilities and amplitudes, of waves that represent possibilities, not certainties, until interactions occur that fix outcomes. When we say an electron is a wave before we look, we do not mean it is a water wave you could splash your hand through. We mean its behavior is described by a mathematical object that spreads out, interferes, and carries the chance of being found here or there. The moment we involve measuring devices, the probabilities crystallize, and we find a definite spot. For much of the 20th century, the working story was simple and practical. Do the math of wave behavior to predict experimental results, and do not ask too many questions about what is really happening between preparation and measurement. This was sometimes called the Copenhagen interpretation. It was useful. It was quiet about metaphysics. But not everyone was satisfied. In 1957, a graduate student named Hugh Everett wrote a bold thesis. He proposed that the wave never truly collapses. Instead, it keeps evolving smoothly. When a measurement happens, the combined system of electron and detector and scientist becomes entangled. The amplitudes that describe the electron split into branches that no longer talk to each other. In one branch, the electron is found at one spot. In another branch, it is found at another. Each branch contains a version of the observer who finds a definite result. The branches are all real. They simply cease to interfere because information about them has become spread out into the environment. It is like a song that splits into harmonies that drift apart in a wide hall and can no longer recombine. This is the many worlds interpretation. It does not add new equations. It removes an extra rule about collapse. It says the universe always obeys the same smooth quantum evolution. When you look closely, what seemed like abrupt changes are really the branching of entangled states. The feeling of collapse is the feeling of living in one branch. The parallel universes here are not far away in space. They are parallel in possibility space, each containing a full narrative of events consistent with one outcome of every quantum process. Is this science or philosophy? It is both. Carefully. Many worlds makes the same experimental predictions as other interpretations, at least within the domain we can test. It does not lead to a different number on a screen, but it offers a different picture of what is real. That picture is supported by a concept called decoherence, developed in detail by physicists like H. Dieter Zia and Wojciech Zurek. Decoherence explains, with calculations, how interactions between a system and its environment cause quantum superpositions to spread and become effectively classical. The environment acts like a million tiny detectors, constantly touching, constantly carrying away information. This process is fast and relentless for macroscopic objects. That is why we do not see cats both alive and not, tables in two places at once. The world is saturated with information exchange that separates branches and hides interference. There have been beautiful experiments to stretch quantum behavior to larger and larger scales. Interference has been observed not only with electrons and photons, but with molecules made of dozens, hundreds, even thousands of atoms. In carefully isolated vacuum chambers, with temperatures near absolute zero, fragile matter waves can be made to create patterns. These experiments do not prove many worlds, but they strengthen the idea that quantum superposition is a universal principle, limited in practice by decoherence, not in principle by size. The line between quantum and classical is not a sharp boundary. It is a gradient of susceptibility to environmental whispers. Consider also delayed choice experiments, where scientists decide whether to observe which path information after a particle has already passed through a slitted barrier. The outcomes align perfectly with quantum rules. They do not suggest retroactive magic. They suggest that what can be known and what can interfere are connected in subtle ways. If you erase the information that distinguishes the paths, interference can reappear, even if your choice to erase or keep that information is made late. The world seems built from relationships, not from absolute properties that exist independent of context. Layer this with cosmology, and parallel universes gain texture. The physicist Max Tegmark proposed a simple ladder. Level 1, distant regions of the same space. Level 2, bubble universes from eternal inflation, possibly with different constants or forms of physics. Level 3, many worlds arising from quantum branching in the same underlying space. Level 4, mathematical universes, where any mathematically consistent structure exists as a kind of reality. Levels I and II are parts of cosmology. Level 3 comes from quantum mechanics. Level 4 walks into philosophy. Each level builds on ideas we already need to explain what we see. None of them is proven in the way a bridge is proven by holding the weight of a truck. Each is a quiet extrapolation. The many worlds picture invites a feeling. If every quantum event branches, then there are versions of you who chose differently, or rather, versions of the world in which different outcomes were realized. Maybe one branch where you turned left on a quiet street, and one where you turned right. That does not mean you can move between them. It does not mean choices are meaningless. The branches do not mingle. What it might mean is that chance is not the crack or uncertainty sneaks into a deterministic universe. It is the way reality allocates amplitude to different futures, each as real to its inhabitants as ours is to us. If this makes you feel strange, let the feeling rest. It is not necessary to believe many worlds to appreciate its elegance. It makes no new predictions. So many physicists prefer to stay with interpretations that talk only about measurement outcomes. Others find the simple, unbroken evolution soothing. The debate is not about data. It is about description. There is a gentle echo between these ideas and the earlier multiverse of cosmology. In level 2, different bubble universes could have different values of fundamental numbers, like the mass of the electron or the strength of forces. This could emerge from deeper theories where those values are set by the shape of hidden spaces or the state of fields. In level 3, different branches share the same laws, but they explore every outcome those laws allow. Here, parallel universes are not far away. They are right next door in the space of amplitude. Two melodies playing at once, but we only hear the one that involves us, because decoherence has carried the other away into silence we cannot reverse. Now listen for a low hum in the background of the universe. Inflation did not just smooth things out. In many models, it keeps going. It births pockets forever. If that is so, then the variety of what exists might be wider than we can imagine. Different constants, different particles, maybe even different numbers of large dimensions. To see how this could be, we have to look at theories where space has more structure than what our senses reveal. We have to imagine the early universe not as a blank, but as a landscape with many valleys, where the cosmos can rest in different ways. That landscape has a name. It comes from string theory, from compact spaces curled too small to notice, from brains that could brush each other and spark fire. The ideas are bold and evolving. Their poetry is not proof, but they have left us with a picture that, if true, would make the multiverse not a luxury, but a necessity. We will walk into that landscape next, quietly, careful not to claim more than is known. Careful to enjoy the view without insisting it is the only one. Imagine a field that fills all of space, like a mist you cannot see. Its energy depends on where it sits in a potential, a kind of cosmic topography. Inflation can be driven by such a field, often called the inflaton in models. If the field is high up on its potential, the energy density is nearly constant. This acts like a gentle pressure that makes space expand exponentially fast. Like dough in an oven, the distances between points double and double again, smoothing out irregularities, stretching the universe flat. In some models, the field can roll down and inflation ends in our region, releasing energy that becomes particles and radiation. The Big Bang fireball is not the very beginning, but the end of inflation. In other models, random quantum fluctuations jostle the field in different regions. While it rolls down in some places, it is kicked back up in others. Inflation ends here and there, but not everywhere. This is eternal inflation. The regions where inflation ends become bubble universes, hot and expanding in their own right. Between bubbles, inflation continues, keeping them apart with ever-growing space. These bubbles are not embedded in an existing space like soap bubbles in air. They are parts of the fabric of space-time itself, each with its own story. Now add string theory to the canvas, not as a finished painting, but as a library of possibilities. String theory suggests that at the smallest scales, the building blocks of nature are not point particles, but tiny strings vibrating in multiple dimensions, some of which are curled up compactly. The shape of those curled dimensions can determine the properties of particles and forces in a lower dimensional world like ours. There are many ways to curl these dimensions, many ways to stabilize the shapes with fields and fluxes. The resulting menu of possible low-energy universes is called the landscape. It may be vast. Different valleys in this landscape could give rise to different constants of nature. Eternal inflation could explore these valleys, landing in one or another, creating regions where physics looks different in detail, though the basic language of quantum fields remains. This picture, if taken literally, hints that the small value of the cosmological constant, the energy of empty space that causes our universe's expansion to accelerate, might be one selection among many. Most values would not allow galaxies and stars to form. A few do. We should not be surprised, then, to find ourselves in a region with a value that permits complexity. This is an anthropic selection, not an explanation in the usual sense, but a filter. The physicist Steven Weinberg used this reasoning in the 1980s to predict that the cosmological constant would be non-zero but small before it was observed. When the accelerated expansion was discovered in 1998, the idea gained weight. It remains controversial because it replaces a sharp calculation with a distribution and a selection effect. But it lives naturally in a multiverse where many values exist and only some observers do. If bubbles are out there, can they bump? In principle, a collision between two bubble universes could leave an imprint on the cosmic microwave background in the form of a circular pattern or a hemispherical asymmetry. Scientists have searched the data for such signatures. Tempting hints have appeared and faded under scrutiny. As of now, no clear evidence of a bubble collision has been confirmed. Inflation also predicts a spectrum of primordial gravitational waves, ripples in spacetime from its rapid expansion. Detecting a particular pattern in the polarization of the microwave background would be a smoking gun. A few years ago, a claimed detection excited the world, then resolved into dust in our own galaxy. The search continues with quieter patience. Cosmology is careful. Every bold idea must brush against data. The Planck satellite has mapped the microwave sky with precision and finds it remarkably consistent with a simple inflationary picture. The spectrum of fluctuations is nearly scale invariant, with a slight tilt, just as many inflationary models predict. Non-Gaussianities, subtle fingerprints of interactions, are constrained tightly. The universe appears very flat. Alternatives to inflation, like bouncing or cyclic models, exist and are studied. They also produce testable consequences. The multiverse is not a trophy on a shelf. It is a space of models, some of which touch what we can measure, and some of which float beyond for now. Let us also touch a quieter corner, the measure problem. If the global picture contains an infinite number of events in an infinite space, how do we assign probabilities? How do we say this kind of region is common or rare when there are infinitely many of each? Different ways of cutting up the infinite give different answers. This is not a mere technicality. It matters for making any predictions in a multiverse with eternal inflation. Physicists have proposed various measures, each with pros and cons. This problem is not settled. It encouraged humility. There is a more unsettling whisper. In a universe that continues forever and contains thermal fluctuations, rare but inevitable, One can imagine a self-aware fluctuation, a mind arising spontaneously from chaos with false memories. Such a thing is called a Boltzmann brain. If the multiverse is dominated by these random fluctuations, then most observers would be Boltzmann brains, which contradicts our sense of living in an ordered world with a long history. Many cosmologists view this as a red flag. A healthy multiverse should not be overrun by freak observers. This motivates models where ordinary cosmological histories like ours are common and freak observers are rare. Again, the measure matters. Step back and breathe. Many words, many worlds. What do we know? We know that our observable universe is large, expanding, and remarkably uniform on big scales, with tiny seed fluctuations. We know that inflation offers a coherent way to explain this, and has passed several observational tests. We know that quantum mechanics describes experiments with stunning accuracy, and that decoherence explains why we see a classical world emerge from quantum rules. We do not know whether inflation is eternal. We do not know the correct way to evaluate probabilities in such a picture. We do not know which, if any, version of string theory describes our world. We do not know whether many worlds is the truest description of quantum reality, or simply a clean story among several equivalent ones. Other ideas whisper too. In some models, our universe could be a three-dimensional brain floating in a higher dimensional space, and other brains could be other universes. Collisions between brains could ignite big bangs. In cyclic models, the universe might go through endless rounds of contraction and expansion, each producing new conditions. In loop quantum cosmology, quantum gravity effects might replace the Big Bang singularity with a bounce. These visions are being explored, tested where possible, refined where needed. They add to the quiet chorus that says reality might be more layered than the surface suggests. There is even a question about whether our universe is simulated. This question belongs to philosophy and computer science as much as physics. If an advanced civilization could simulate conscious beings within a universe, and if simulated universes vastly outnumber base realities, perhaps we are in one. There is no evidence we are, and no agreed way to test it decisively. Still, the idea reminds us that there are ways to imagine multiplicity beyond physics, and that caution is good. Speculation can inspire. It should not replace the tenderness of asking nature and listening patiently for her answer. Pause and feel the steadiness underneath. The multiverse, in its different forms, is not a conspiracy of cosmic excess. It is a set of honest consequences from ideas that already work. An infinite space generates distant copies. Inflation naturally spawns new regions. Quantum mechanics naturally creates branches of outcomes. Mathematics, taken as ontology, supports many structures. We do not need to believe all or any of these are physically realized to appreciate their coherence. We can hold them gently and let them illuminate our sense of scale and possibility. What do these discoveries mean for us? If there are many universes, how should we live? What matters? The science does not answer that directly, but it gives us metaphors that soften the heart. That is where we go next. Into meaning. Into the quiet room where the stars above and the thoughts within gently meet. If the universe is single, we are small and precious. If the universe is plural, we are small and precious too. The number does not change the feeling of sitting by a window at night and hearing rain. It does not change the way laughter echoes in a kitchen, or the way a hand finds another hand and fits. Science, at its best, does not make our lives abstract. It makes them vivid. It shows us that every moment is carved by deep rules and bright accidents, by forces and by fragile probabilities. Parallel universes, in any form, ask us to widen our imagination, to accept that what we cannot see might be real, to accept that our observable bubble is not the whole, that our branch of events is one of many allowed by the quantum score. This does not belittle us. It invites humility without erasing meaning. Your choices matter because you live them. They are the way your branch sings. They shape the world around you, the people you love, the ripples you leave. In a multiverse, kindness is not diluted. It is repeated. Each act is still a light in one room. There is comfort in the quiet neutrality of physical law. Gravity does not aim. Quantum fields do not judge. They simply are. Within that restless order, complexity blooms. Atoms become stars. Stars forge carbon. Carbon learns to dream. Over billions of years, on at least one world, matter rearranged itself into beings who ask whether there are other worlds nearby or far. It is beautiful and strange that the laws of physics allow minds to rise and then wonder about the laws themselves. Consider the simplest multiverse again. If space is infinite, there may be distant regions where the pattern repeats. Somewhere a night sky looks the same. Somewhere a deep-sea jelly drifts in a bioluminescent cloud that seems familiar. In those regions, the physics is our physics. The same constants. The same chemistry. Many worlds adds a different kind of mirror. In those branches, the rules are the same, but the outcomes vary. A coin lands differently. A neuron fires at another time. You do not need to feel that your identity is spread thin by this. Identity is lived in sequence, here, within a single history. The existence of other histories does not take yours away. It simply places it in a larger pattern where all that can happen under the rules will happen with the right weight. The deeper multiverse of eternal inflation and the string landscape is more remote. It speaks to the underlying structure of physics. If it is correct, then what we call the fundamental constants are local customs, chosen by where we live in the landscape. That idea is both unsettling and liberating. Unsettling because it moves parts of physics from necessity to contingency. Liberating because it explains why some numbers are what they are, without demanding a single calculation to fix them. Instead of asking why this value, we might ask why any value that allows life is observed, and then check whether our value is typical among those. This is a delicate business. It can lead to sloppy reasoning if we are not careful. Scientists are careful. They test what can be tested and admit when a question is beyond reach for now. If the multiverse remains a possibility rather than a fact, what is the value in thinking about it? The value is in the way it sharpens our questions. It helps us separate what must be true everywhere from what might be true somewhere. It invites new kinds of observations, like searches for bubble collision patterns, or for primordial gravitational waves. It guides particle physics by hinting that some parameters may not be uniquely determined, which influences how we look for unified theories. And beyond utility, it nourishes a gentle awe. That awe is not a conclusion. It is a companion. Sit with your breath for a moment. Inhale slowly. Think of the microwave background, a whisper of light older than any star, bathing you now. Exhale slowly. Think of quantum interference, a ripple of possibility that becomes a point on a screen. In between, there is you, a being who can hold both the very large and the very small in one mind. That is not trivial. It is a quiet triumph of a universe that became conscious of itself through you and through others like you. There are worries we can let go of. If there are uncountable worlds, does that make this one less special? No. Special is not a count. It is a relation. This world is special to you because it is yours. Your sunrise is yours, and even if 1,000,000,000,000 sunrises happen elsewhere, the warmth on your skin is not elsewhere. It is here. If many worlds exist, do they make our science unfalsifiable? No. We still test. We still predict. We still listen to the sky and to our instruments. The multiverse does not end science. It extends the space of ideas science considers. There is also a quiet acceptance that some questions may not have crisp answers we can reach soon. That is all right. Science is patient. It took centuries to understand starlight. We can take our time with the multiverse. Along the way, we can appreciate the view. The idea that reality might be layered, that nature may be more generous than any single universe requires, is a source of wonder. Wonder is fuel. It keeps curiosity soft and alive. As you drift toward sleep, imagine standing on a shore at night. The ocean is calm. Somewhere beyond the horizon, there may be other coastlines, other lanterns, other people listening to quiet waves. Somewhere in a laboratory, a single particle meets two slits and teaches the world to breathe between probabilities. Somewhere in the early universe, fields roll and bubble, stitching pockets of space into being. And here, in this room, on this earth, you are present. You are part a whole. Not by accident, not by design, but by a chain of events both delicate and vast, faithful to laws that carry a kind of austere kindness in their neutrality. Thank you for wandering through this with me tonight. If you would like to live in this gentle space more often, to fall asleep with stories of science and wonder, you are welcome to subscribe and stay close. We will keep exploring softly, one quiet universe at a time.